23 million years ago, light left a galaxy so beautiful that when humans finally saw it, they named it after swirling water. That light has been traveling toward Earth since before our ancestors walked upright. Tonight, if you point a telescope at a tiny patch of sky near the Big Dipper, you will see something that rewrote astronomy forever. The Whirlpool Galaxy was the first cosmic object where humans recognized the spiral structure that defines our own Milky Way. It contains over 100 billion stars, a supermassive black hole, and possibly the first planet ever detected outside our galaxy. If you want to journey 23 million light-years and witness the most photographed galaxy in human history, hit that like button and subscribe. For now, get comfortable. Let's begin. The year was 1773, and a French astronomer named Charles Messier was hunting comets. These icy wanderers represented the most prestigious discoveries an astronomer could claim in the 18th century. A new comet meant headlines in scientific journals. It meant letters of congratulation from colleagues across Europe. It meant your name attached to a celestial object for eternity. Messier had already discovered several comets and earned the nickname the Ferret of Comets from King Louis XV himself. But Messier faced a frustrating problem that plagued every comet hunter of his era. The night sky contained numerous fuzzy patches that looked exactly like distant comets but never moved. These stationary smudges wasted precious observation time. Messier would spot a faint glow through his telescope, feel his pulse quicken with anticipation, and begin tracking the object across subsequent nights. A real comet would shift position against the background stars as it travelled through the solar system, but these fuzzy imposters remained fixed, night after night, mocking his efforts. Each false alarm cost hours of careful observation that could have been spent finding genuine comets. Messier decided to transform his frustration into something useful. He would catalogue these nuisances, creating a comprehensive list of objects that comet hunters should ignore. If he documented the position and appearance of every fuzzy blob that was not a comet, future astronomers could consult his list and avoid wasting time on the same stationary objects. The catalogue would serve as a warning guide, marking celestial locations where deceptive smudges lurked. On October 13, 1773, Messier pointed his telescope toward the constellation Canes Venatici, the hunting dogs. This small constellation lies just below the handle of the Big Dipper, a region of sky that passes nearly overhead for observers in the northern hemisphere. There he found another faint nebulous patch, barely visible even through his instrument. He recorded its position carefully, noted its fuzzy appearance, and labelled it Messier 51. Just another blob to avoid. The entry in his catalogue was brief and dismissive, describing an unremarkable smudge that would only distract serious comet hunters. Messier could not have known this supposed nuisance would become one of the most important astronomical objects ever discovered. He could not have imagined that 250 years later, the most powerful space telescope ever constructed would spend days photographing this particular fuzzy patch. He certainly never suspected that within that faint glow lay over 100 billion stars, countless planets, a supermassive black hole, and possibly the first world ever detected beyond our own galaxy. The object he dismissed as an annoyance would eventually rewrite human understanding of cosmic structure. Messier continued adding objects to his catalogue throughout his career, eventually documenting 110 celestial nuisances. These Messier objects, as they became known, include some of the most famous astronomical targets visible from Earth: the Orion Nebula, the Andromeda Galaxy, the Crab Nebula, and dozens of star clusters all bear Messier designations. The irony runs deep. A catalogue created to help astronomers ignore distracting objects became one of the most important observing guides in astronomical history. Amateur astronomers today compete to observe all 110 Messier objects, treating the list as a cosmic scavenger hunt rather than a warning of things to avoid. But in 1773, Messier 51 was simply entry number 51 on a list of fuzzy patches. No one knew what it actually was. No one possessed the technology to find out. For 72 years, Messier's fuzzy blob remained a mystery. Astronomers debated what these nebulous patches might be, but the debates generated more heat than light. Some believed they were clouds of gas within our own stellar system, perhaps regions where new stars were forming from condensing material. This view seemed reasonable given the era's understanding of physics. Others speculated they might be distant collections of stars too far away to resolve individually, their combined light blurring into a smooth glow. A few radical thinkers proposed that some nebulae might be separate star systems entirely. Island universes comparable to our own Milky Way, but located at distances beyond imagination. The technology to settle this debate simply did not exist. Telescopes of the era could magnify these objects, but could not reveal their true nature. The fuzzy patches remained fuzzy no matter how much magnification astronomers applied. Larger telescopes gathered more light, making the objects brighter and easier to study. But they could not resolve the smooth glow into individual components. The limitation was fundamental. These objects were either intrinsically smooth, like gas clouds, or composed of stars so numerous and distant that no telescope could separate them. The spiral nebulae, as they would later be called, kept their secrets hidden behind the limitations of 18th century optics. Astronomers could measure their positions with precision. They could describe their appearances in careful detail. They could speculate endlessly about their nature, but they could not determine whether these mysterious objects lay thousands of light years away or millions, whether they contained gas or stars, whether they were small nearby clouds or vast distant structures. This uncertainty persisted for decades. Generation after generation of astronomers observed the nebulae, catalogued new examples, and argued about interpretations. Scientific papers proposed contradictory theories. Observations that seemed to support one view were countered by observations supporting another. The nebula debate became one of the great unresolved questions in astronomy, a puzzle that refused to yield to the observational techniques available. The breakthrough came in 1845 when an Irish nobleman named William Parsons, known as Lord Rosse, completed construction of the largest telescope the world had ever seen. Lord Rosse was not a professional astronomer. He was a wealthy aristocrat with a passion for science and the resources to pursue that passion on a grand scale. His family estate at Birr Castle in central Ireland became the site of an astronomical project that pushed the boundaries of what was technically possible. The telescope Lord Rosse constructed earned the nickname the Leviathan of Parsonstown after the nearby town. Its primary mirror measured 72 inches in diameter, dwarfing every other telescope in existence. The mirror alone weighed nearly 4 tons and required years to cast, grind, and polish to the precise curvature needed to focus starlight. The mounting structure rose to the height of a 6-story building, with massive stone walls on either side to support the enormous tube. Building such an instrument required solving engineering problems no one had tackled before. The mirror was made of speculum metal, an alloy of copper and tin that could be polished to reflect light but tarnished quickly in the damp Irish climate. Lord Rosse built a second mirror of identical size so that one could be in use while the other was being repolished. The mounting allowed the telescope to swing only in a narrow arc of sky on either side of the meridian, a compromise necessary to support such tremendous weight. Observing any particular object required waiting until it passed through the accessible region of sky. Despite these limitations, the Leviathan gathered more light than any previous instrument. When Lord Rosse pointed this unprecedented telescope toward Messier's fuzzy blob on a clear night in 1845, he witnessed something no human had ever seen before. The nebulous patch resolved into a distinct pattern. What had appeared as a formless smudge through smaller telescopes now revealed intricate structure, graceful arms curved outward from a bright central core, sweeping through space like water draining from a cosmic basin. The resemblance to a whirlpool was unmistakable. Lord Rosse was looking at something that had definite shape, definite organization, definite architecture. He had discovered spiral structure in a celestial object for the first time in human history. The moment must have been extraordinary. For 72 years, astronomers had wondered what the fuzzy patches really were. Theories had multiplied without resolution, and now, in a single observation, Lord Rosse had revealed that at least some of these objects possessed complex structure that demanded explanation. This was not a formless cloud of gas. This was something with arms, with a core, with a pattern that suggested rotation and organization on a vast scale. Lord Rosse made careful drawings of what he observed. These sketches, created at the eyepiece during long, cold nights of observation, captured the spiral pattern with remarkable accuracy. When his drawings were later compared to modern photographs, the correspondence was striking. Lord Rosse had accurately recorded features that would not be photographed for another half-century. He published his observations and detailed drawings, and these illustrations spread throughout the scientific community. The Whirlpool pattern gave the object its common name, which persists to this day. The Whirlpool Nebula, later the Whirlpool Galaxy, entered astronomical vocabulary as the first spiral structure ever recognized in the heavens. The discovery sparked intense debate about the nature of spiral nebulae. The spiral pattern demanded explanation. What physical processes could create such organized structure? Were these objects nearby gas clouds, perhaps solar systems in the process of forming, as matter spiraled inward toward a central condensation? This interpretation appealed to astronomers who favored the nebula hypothesis, the idea that our own solar system had formed from a rotating disk of material that gradually collapsed. Or were spiral nebulae something far more extraordinary? Some astronomers began to wonder whether these objects might be external star systems, comparable to our own Milky Way but located at distances so enormous that individual stars blurred together into smooth light. The spiral arms might represent regions of concentrated stars, with the overall pattern revealing the structure of vast rotating collections of suns. The idea that spiral nebulae might be separate galaxies, each containing billions of stars at distances beyond comprehension, seemed too radical for most astronomers to accept. The required distances were staggering. If spiral nebulae were truly comparable in size to the Milky Way, they would need to be millions of light-years away to appear as small as they did in the sky. Such distances exceeded anything astronomers had previously contemplated. They challenged fundamental assumptions about the scale and structure of the universe. This debate would consume the scientific community for another 80 years. Observations accumulated on both sides. Some measurements seemed to show that spiral nebulae were rotating, which would support the idea that they were relatively small and nearby. Other observations detected what appeared to be individual stars within the spirals, suggesting they might be distant stellar systems after all. The Great Debate, as it became known, remained unresolved into the 20th century. The resolution came in 1923 when Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory in California to study the Andromeda Nebula. This instrument, the largest in the world at that time, gathered enough light to resolve individual stars within the spiral structure. Hubble focused on a particular type of star called a Cepheid variable. Cepheid variables are pulsating stars that brighten and dim in regular cycles. The crucial property of Cepheids, discovered by astronomer Henrietta Swan-Leavitt in 1912, is that their pulsation period relates directly to their intrinsic brightness. A Cepheid that pulses with a longer period is genuinely more luminous than one with a shorter period. By measuring how quickly a Cepheid pulses, astronomers can determine how bright it actually is. Comparing this intrinsic brightness to how bright the star appears in the sky reveals its distance. Hubble identified Cepheid variable stars within the Andromeda Nebula. He measured their pulsation periods carefully over many nights of observation. Then he applied Leavitt's period-luminosity relationship to calculate their distances. His results were shocking. The Cepheids in Andromeda were far too distant to lie within our Milky Way. They were located hundreds of thousands of light-years beyond the boundaries of our own galaxy. The implications were revolutionary. The Andromeda Nebula was not a nebula at all. It was a separate galaxy, an island universe containing billions of stars entirely distinct from the Milky Way. And if Andromeda was an external galaxy, then other spiral nebulae almost certainly were as well. The Whirlpool Galaxy, that fuzzy nuisance Charles Messier catalogued to help comet hunters avoid wasting time, was revealed as a cosmic structure of almost incomprehensible scale. It was not a cloud of gas within our stellar neighborhood. It was a vast, rotating system of stars located millions of light-years from Earth. Within its spiral arms burned over 100 billion stellar furnaces, each potentially hosting planets, each representing a nuclear reaction, converting mass into energy across cosmic time. Hubble's discovery transformed human understanding of the universe overnight. Before 1923, most astronomers believed the Milky Way essentially constituted the entire cosmos. Yes, fuzzy patches dotted the sky, but they were thought to be minor features within or near our own stellar system. After 1923, astronomers understood that our galaxy was merely one among countless others. A single island in a vast cosmic archipelago, stretching to distances that challenged comprehension. The scale expansion was staggering. The universe went from being a few 100,000 light-years across, roughly the size of the Milky Way, to being millions and eventually billions of light-years in extent. Every spiral nebula became a galaxy. Every galaxy contained billions of stars. The cosmos had grown by factors that rendered previous conceptions obsolete. Modern measurements place the Whirlpool Galaxy between 23 and 31 million light-years from Earth. The uncertainty in this range reflects the genuine difficulty of measuring cosmic distances across such gulfs of space. Different techniques yield slightly different results, and astronomers continue refining their measurements as instruments improve. For most purposes, the distance is cited as approximately 23 million light-years, placing M51 among the closer galaxies beyond our immediate local group of neighboring systems. A light-year represents the distance that light travels in 1 year, moving at approximately 670 million miles per hour. This velocity is difficult to grasp in human terms. Light could circle the entire Earth 7.5 times in a single second at this speed. A beam of light could travel from Earth to the Moon in just over 1 second. It could reach the Sun in about 8 minutes. Light crosses the entire span of our solar system in a matter of hours. Yet even at this tremendous velocity, light requires 23 million years to cross the void between the Whirlpool Galaxy and our planet. That journey time exceeds human comprehension. When those photons left their source in M51, our ancestors were small primates living in African forests. The genus Homo did not yet exist. Evolution had not yet produced the lineage that would eventually develop language, art, science, and telescopes capable of capturing those ancient photons. The entire span of human evolution fits within the travel time of light crossing the distance to this single galaxy. Every ancestor you have ever had, stretching back through hundreds of thousands of generations to creatures that would be unrecognizable as human. Stone tools, fire, language, agriculture, cities, writing, mathematics, physics, and space telescopes, all developed during the interval between a photon's departure from M51 and its arrival at human instruments. This temporal span creates a kind of cosmic humility. It has been traveling through the void since before anything resembling a human existed anywhere in the universe. We are recent arrivals in a cosmos that operated for billions of years before us, and continues operating without any regard for human timescales. The impossibility of physical travel to the whirlpool deserves careful consideration. Science fiction has conditioned us to imagine journeys between stars and galaxies as difficult but achievable challenges. Characters hop between stellar systems in hours or days, crossing distances that would require generations in reality. The actual physics of interstellar and intergalactic travel offers no such convenience. The fastest spacecraft humans have ever built is the Parker Solar Probe, a NASA mission designed to study the Sun from close range. During its closest approaches to the Sun, the probe reaches peak speeds of approximately 430,000 miles per hour, accelerated by the Sun's enormous gravity. This is the fastest any human-made object has ever traveled. At that velocity, traveling continuously without slowing down for any reason, a journey to the Whirlpool Galaxy would require roughly 40 trillion years. This number defies comprehension, but we can place it in context. The universe itself is only 13.8 billion years old. 40 trillion years is approximately 3,000 times the current age of the entire cosmos. You would need to wait for the universe to reach 3,000 times its present age before a spacecraft traveling at Parker Solar Probe speeds could reach M51, and this calculation assumes continuous travel at maximum velocity, which is itself impossible. The Parker Solar Probe reaches its peak speed only during brief close passes to the Sun. Maintaining such velocity in deep space would require propulsion systems that do not exist. Accelerating to such speeds in the first place would require energy expenditures beyond current or foreseeable technology. The Whirlpool Galaxy exists forever beyond human reach in any physical sense. No spacecraft we could build with known physics could carry humans across such a distance within any meaningful time frame. Even messages traveling at the speed of light would require 23 million years to cross the void, and another 23 million years for any reply. Communication is as impossible as travel. The only access we have to the Whirlpool comes through the ancient photons that complete their 23 million year journey to our telescopes each night. Light carries information about its source. By analyzing this light with sophisticated instruments, astronomers can determine the chemical composition of distant stars, measure their temperatures, track their motions, and infer the physical processes occurring within distant galaxies. All our knowledge of M51 comes from decoding the information carried by photons that have wandered through intergalactic space since before our species existed. This cosmic distance creates one of astronomy's strangest confirmed facts. When you observe the Whirlpool Galaxy through a telescope, you are not seeing it as it exists tonight. You are looking 23 million years into the past. The galaxy you observe is an ancient version that has continued evolving during the impossibly long interval since that light departed. Stars visible in our photographs may have exploded as supernovae in the intervening millions of years. New stellar nurseries may have ignited in regions that appear dark in our images. Planets may have formed around stars that were young when the light we see departed. Civilizations, if any exist in M51, may have risen and fallen many times during the journey of the photons now reaching Earth. The gravitational dance between the Whirlpool and its companion galaxy has progressed significantly since the light we observe tonight was emitted. The companion has moved along its orbit. The spiral arms have rotated, density waves have propagated through the disk, and countless individual stars have shifted their positions. The galaxy we observe is not the galaxy that exists. We see an ancient cosmic artifact preserved in photons, a snapshot of a moment 23 million years past. We cannot know the current state of the Whirlpool Galaxy. That information travels at the speed of light, which means the current news about M51 will not reach Earth for another 23 million years. By then, of course, human civilization in any recognizable form may have long since disappeared. The information asymmetry is permanent and insurmountable. We are forever limited to studying the past while the present remains hidden behind the light travel time barrier. This temporal displacement affects all astronomical observations, but the effect becomes significant only at cosmic distances. Observations of objects within our solar system show them essentially as they exist now, with light travel times measured in minutes or hours. Observations of nearby stars show them as they were years or decades ago. The nearest star system, Alpha Centauri, appears as it was about 4 years in the past. Stars visible to the naked eye range from a few years to a few thousand years in the past. But external galaxies push this displacement to extremes that challenge intuition. The Whirlpool, at 23 million light-years, represents relatively nearby cosmic history. Galaxies billions of light-years away show us conditions that existed when the universe was young, when the Sun and Earth had not yet formed, when the chemical elements necessary for rocky planets and life were still being manufactured in stellar furnaces. Astronomy is inherently a historical science. We study the past by necessity, examining light that departed its sources long before arriving at our instruments. The further we look into space, the further we look back in time. The deepest observations peer into cosmic epochs billions of years past, showing us a young universe dramatically different from present conditions. The Whirlpool's orientation relative to Earth made it uniquely valuable for astronomical study. A fortunate geometric accident that has transformed our understanding of spiral structure. We observe M51 almost directly down its rotational axis, seeing the galaxy nearly face on. This geometry presents the spiral structure as if the galaxy were deliberately posing for cosmic portraits. Consider the alternative views. Galaxies oriented edge-on to our line of sight appear as thin streaks of light, their spiral arms compressed into a line and largely hidden behind obscuring dust lanes concentrated in the galactic disk. The spiral structure cannot be studied directly because we see only the galaxy's profile. Galaxies tilted at intermediate angles display elliptical shapes with distorted spiral patterns, the geometry warping our view of the underlying structure. The Whirlpool escaped these viewing limitations. Its nearly face-on orientation spreads the spiral arms across our field of view, allowing astronomers to trace them from the central core outward to the galactic edges. Dust lanes appear as dark streaks crossing the bright stellar background, rather than obscuring the entire disk. Star-forming regions glow pink along the arm edges. Young stellar clusters burn blue in the interarm spaces. The entire structure lies open to inspection. This favourable geometry, combined with the galaxy's relative proximity among systems beyond our local group, has made M51 one of the most intensively studied objects in extragalactic astronomy. Every major telescope built in the past century has photographed the Whirlpool, each instrument revealing new aspects of a structure first sketched by Lord Rosse in 1845. Ground-based observatories captured increasingly detailed optical images as telescope size and photographic technology improved. The Hubble Space Telescope, orbiting above Earth's blurring atmosphere, produced images of astonishing clarity, showing individual star-forming regions and dust structures. The Chandra X-ray Observatory revealed high-energy phenomena invisible to optical instruments. Radio telescopes mapped hydrogen gas distributions throughout the spiral arms. And most recently, the James Webb Space Telescope produced infrared observations that peer through dust to reveal structures hidden from all previous instruments. The Whirlpool has become a laboratory for testing theories of spiral structure and galactic evolution. Because we can see it so clearly, we can compare theoretical predictions against observed reality in detail, impossible for galaxies viewed at less favourable angles. Models of density wave propagation, star formation triggering, and galactic interaction can be tested against the rich observational data accumulated over more than a century and a half of study. Lord Rosse could not have imagined what his sketches would eventually inspire. He saw spiral structure for the first time and recognized its significance, that this particular object would become a cornerstone of modern astrophysics. The fuzzy blob that annoyed Charles Messier, the spiral nebula that puzzled Victorian astronomers, the external galaxy that confirmed cosmic scales beyond imagination, and the modern research target photographed by space telescopes costing billions of dollars are all the same object, viewed through evolving instruments and accumulating knowledge. The Whirlpool has witnessed the entire arc of human astronomical progress. Each generation of scientists has approached it with better tools and deeper questions. Each generation has learned something new about a structure that guards secrets still waiting for instruments not yet built and questions not yet formulated. 23 million light-years of distance separate us from answers that transform our understanding of cosmic structure. The light arriving tonight has travelled since before our species evolved, carrying information about stellar nurseries, spiral dynamics, and galactic interactions across a gulf of space that will never be crossed by human travellers. What does that ancient light reveal about the structure of the whirlpool? What physical processes create those elegant spiral arms? Why does this particular galaxy display such pronounced patterns when many other spirals show ragged, poorly defined structures? The answers involve cosmic forces operating across scales that dwarf anything in human experience. The whirlpool's beauty emerges from gravitational interactions that have been reshaping two galaxies for hundreds of millions of years. What appears serene and elegant in photographs actually represents one of the most dynamic interactions occurring in our cosmic neighborhood. The anatomy of the whirlpool awaits examination, revealing how gravity, gas, dust, and dark matter combine to create one of the most beautiful structures in the observable universe. The Whirlpool Galaxy belongs to a special category that astronomers call grand design spirals. This classification describes galaxies with prominent, well-defined spiral arms that can be traced continuously from the galactic core to the outer edges. The arms sweep outward in elegant curves, maintaining their coherent structure across tens of thousands of light-years. When Lord Rosse first sketched M51 in 1845, he was observing one of the finest examples of this galactic architecture anywhere in the observable universe. Grand design spirals are surprisingly rare. Only 10 to 30% of spiral galaxies display such organized structure. The majority of spirals show ragged, poorly defined arms that fragment and blur as they wind outward from the center. These flocculent spirals, as astronomers call them, possess spiral patterns that appear patchy and discontinuous. Their arms break into segments, branch unpredictably, and fade into the general stellar background without clear boundaries. Compared to these disordered cousins, grand design spirals like the whirlpool appear almost artificially perfect, as if some cosmic architect had drawn their structure with mathematical precision. What makes grand design spirals so rare requires understanding physics that operates on scales almost impossible to visualize. The elegant spiral patterns we photograph are not what they appear to be. Human intuition, shaped by experience with rotating objects on Earth, naturally interprets spiral arms as solid structures spinning like the blades of a pinwheel or the arms of a spinning lawn sprinkler. This intuition is completely wrong. If spiral arms were solid structures rotating around the galactic center, a fundamental problem would destroy them within just a few galactic rotations. The problem is called differential rotation, and it arises from basic orbital mechanics that govern how objects move around massive centers. Consider how orbits work. Objects closer to a gravitational center move faster than objects farther away. Mercury orbits the Sun much faster than Neptune. The Moon orbits Earth faster than distant satellites. This same principle applies to stars orbiting galactic centers. Stars in the inner regions of a galaxy complete their orbits in far less time than stars in the outer regions. In the Whirlpool Galaxy, a star orbiting near the central regions might complete one full circuit around the galactic center in approximately 100 million years. A star located in the outer spiral arms might require 300 million years to complete the same journey. This difference is enormous. Inner stars complete 3 full orbits for every single orbit completed by outer stars. Now, imagine what would happen if spiral arms were fixed structures containing the same collection of stars throughout time. After one galactic rotation, the inner portions of each arm would have traveled much farther around the galaxy than the outer portions. The arms would begin to wind up, wrapping tighter and tighter around the galactic center like thread winding onto a spool. After just a few rotations, the spiral pattern would become so tightly wound that it would essentially disappear, smeared into a featureless disk by differential rotation. This is called the winding problem, and it troubled astronomers for decades after spiral structure was first recognized. Galaxies are billions of years old. They have completed dozens of rotations since their formation. If spiral arms were material structures, they should have wound themselves into oblivion long ago. Yet spiral patterns persist. The Whirlpool displays arms that appear fresh and unwound despite the galaxy's ancient age. Something fundamental was missing from the simple rotating arm model. The solution came from understanding that spiral arms are not solid structures at all. They are density waves, regions of compression that move through the galactic disk like ripples spreading across the surface of a pond. The individual stars and gas clouds that compose the visible galaxy flow through these waves, entering compressed regions, lingering briefly, then exiting to continue their normal orbits. The wave pattern maintains its shape, while the matter composing it constantly changes. This concept requires abandoning intuitive notions about what spiral arms actually are. When you look at a photograph of the Whirlpool, you are not seeing a collection of stars that travel together around the galaxy. You are seeing a region where stars happen to be more concentrated at this particular moment. Different stars will occupy that same region 100 million years from now, while the stars currently there will have moved elsewhere. The pattern persists even as its composition completely changes. The traffic analogy helps clarify how density waves operate in practice. Imagine driving on a highway and approaching a congested zone where traffic slows down. Cars entering the congested region must reduce speed because the vehicles ahead are bunched together. After crawling through the slowdown, cars eventually exit the congested zone and accelerate back to normal highway speeds. The individual cars move through the traffic jam, entering at one end and exiting at the other. But the traffic jam itself remains in roughly the same location, a persistent feature of the highway despite being composed of constantly changing vehicles. Spiral arms work according to the same principle. Stars, approaching a density wave experience, enhanced gravitational attraction from the concentrated matter ahead. This gravitational influence causes them to slow slightly as they enter the wave. While moving through the compressed region, stars bunch together, increasing the local density. Eventually, they exit the wave and resume their normal orbital velocities, spreading out again as they leave the compression zone behind. The wave pattern rotates around the galaxy at its own characteristic speed, called the pattern speed. This rotation is slower than the orbital motion of inner stars, but faster than the orbital motion of outer stars. The difference in velocities means that matter continuously streams through the wave from the inner galaxy to the outer galaxy. Stars spend extra time in the compressed region because they slow down there, creating the visual enhancement we observe as spiral arms. This density wave theory, developed primarily by Chinese-American astronomer Chiao Lin and his colleagues in the 1960s, finally resolved the winding problem. Spiral arms can persist for billions of years because they are waves rather than material structures. The wave pattern does not wind up because it rotates as a coherent whole at a single pattern speed, immune to the differential rotation that would destroy material arms. The density wave model makes specific predictions about what we should observe in spiral galaxies. Compressed gas entering the wave should collapse to form new stars. These newborn stars should appear along the inner edges of spiral arms, where gas first encounters the compression. Young stars should then age as they move through the arm, creating a gradient of stellar ages across the arm width. The Whirlpool provides spectacular confirmation of these predictions. The Whirlpool spans approximately 60,000 to 90,000 light-years in diameter, depending on how faint outer regions are measured and which wavelengths are used for observation. Deep exposures reveal tenuous outer structures that shorter exposures miss. Infrared observations detect old, cool stars extending beyond the regions visible in optical light. The range of size estimates reflects these measurement complexities rather than genuine uncertainty about the galaxy's extent. This makes the Whirlpool somewhat smaller than our Milky Way, which measures roughly 100,000 light-years across its stellar disk. The comparison is imperfect because measuring our own galaxy's size from inside is inherently difficult, and different measurement techniques yield different results for both systems. But to first approximation, the whirlpool would fit comfortably within our galaxy's boundaries. A substantial cosmic structure, but not among the largest spirals known. Within this span orbit over 100 billion stars. Each of these stellar furnaces burns through nuclear fuel at rates determined by its mass and composition. Each potentially hosts a planetary system, formed from the same primordial disk of gas and dust that created the star itself. The whirlpool contains enough stars to provide a sun for every human who has ever lived, multiplied by more than 10. The exact stellar count carries significant uncertainty because we cannot resolve and count individual stars at such distances. Even the Hubble Space Telescope, with its exquisite resolution, sees only the brightest individual stars in M51. The vast majority of the galaxy's stellar population blends together into a smooth glow that varies in brightness across the disk, but cannot be separated into discrete sources. Astronomers estimate stellar populations using indirect methods. They measure the total light output of the galaxy across multiple wavelengths. They compare this composite spectrum to theoretical models of stellar populations containing various mixtures of star types. By finding the model that best matches the observed light, they infer how many stars of each type must be present. The technique works but introduces uncertainties that propagate into the final population estimates. The density waves compressing the whirlpool's interstellar medium create a cosmic assembly line visible in detailed photographs from the Hubble Space Telescope and other advanced instruments. Follow a spiral arm from inner to outer regions, and you observe star formation in sequential stages, a spatial progression that corresponds to temporal evolution through the star-forming process. The inner edges of spiral arms show dark lanes of dust and cold molecular gas. This material represents the raw feedstock waiting to be processed into new stars. Giant molecular clouds containing thousands of solar masses of hydrogen drift through the galaxy, slowly approaching the density wave that will trigger their transformation. The clouds appear dark in optical images because the dust mixed with the gas absorbs and scatters background starlight, blocking our view of more distant regions. As molecular clouds enter the density wave, compression increases their density beyond critical thresholds. Gravity begins winning its battle against the gas pressure that previously supported the clouds against collapse. Regions within the clouds start contracting, fragmenting into smaller clumps that will eventually become individual stars or small stellar groups. This compression-triggered collapse is why spiral arms are sites of active star formation. Moving outward along the arm from the dark dust lanes, pink regions mark emission nebulae where star formation has recently concluded. Newborn stars, still embedded in the remains of their natal clouds, pour intense ultraviolet radiation into surrounding gas. This energetic radiation ionizes hydrogen atoms, stripping electrons from protons. When the electrons recombine with protons, they emit light at characteristic wavelengths, including the distinctive red-pink glow of hydrogen alpha emission. These glowing clouds are stellar nurseries, announcing the birth of new suns through their rosy luminescence. Further still along the arm, brilliant blue clusters contain young stars that have cleared away their natal gas clouds. The most massive stars in these clusters burn with surface temperatures exceeding 20,000 degrees, producing the intense blue-white light that dominates the visual appearance of spiral arms. These stellar giants consume their nuclear fuel at prodigious rates, shining with luminosities thousands of times greater than our Sun. Their brief lives, measured in millions rather than billions of years, ensure that they never travel far from their birthplaces before exploding as supernovae. This spatial progression reveals the density wave in action. Different locations along the arm show different stages of the star formation process, corresponding to different times since gas entered the compression zone. The dark dust lanes show gas that has just arrived. The emission nebulae show gas currently collapsing into stars. The entire arm becomes a chronological display of stellar evolution, frozen in space. The Whirlpool's spiral arms glow with particularly intense blue light because an ongoing gravitational interaction has enhanced density waves far beyond what occurs in isolated galaxies. Solitary spirals develop density waves through internal processes, but the resulting patterns tend to be weaker and less organized than what we observe in M51. Something external is driving the Whirlpool's spectacular structure. That something is a smaller companion galaxy designated NGC 5195, appearing at the tip of one spiral arm like a pearl attached to a cosmic necklace. In photographs, this companion seems to be tugging on the larger galaxy, pulling one spiral arm outward toward itself. The visual impression of gravitational interaction is entirely accurate, though the actual geometry is more complex than two-dimensional images suggest. NGC 5195 is a peculiar galaxy in its own right. It lacks the elegant spiral structure of its larger companion, displaying instead a more irregular, disturbed morphology. This irregularity results from the same gravitational interaction that enhances the Whirlpool's spiral arms. The smaller galaxy has been stretched and distorted by tidal forces during its repeated encounters with M51. Its current appearance reflects billions of years of gravitational abuse. The companion contains roughly 1/3 the mass of the Whirlpool. This mass ratio places the interaction in an interesting regime. NGC 5195 is massive enough to significantly affect its larger neighbour, generating gravitational perturbations that propagate through the Whirlpool's disk and enhance spiral structure. But it is not so massive that it would quickly merge with or destroy the larger galaxy. Instead, the two systems engage in an extended gravitational dance that has already lasted hundreds of millions of years and will continue for billions more. NGC 5195 is not merely passing by the Whirlpool in a chance encounter. Computer simulations reveal that this companion approached the Whirlpool from behind approximately 500 million years ago, passing through or near the main galaxy's disk in a dramatic close encounter. This passage was not a gentle graze. The companion plunged through the Whirlpool's outer regions, creating gravitational shocks that propagated inward like ripples from a stone dropped into still water. These gravitational shocks enhanced the density waves already present in the Whirlpool's disk. The compression zones became more pronounced. The spiral pattern became more organized. Star formation rates increased as more gas was swept into the strengthened density waves. The beautiful grand design structure we observe today bears the imprint of that ancient encounter. After passing through the Whirlpool's disk, NGC 5195 continued on its orbit, looping around the larger galaxy in a complex three-dimensional trajectory. The companion did not escape to infinity. Gravitational binding kept it tied to the Whirlpool system, eventually returning it for another close approach. Simulations suggest that a second passage occurred more recently, perhaps 50 to 100 million years ago, further enhancing the spiral structure. Each close encounter between the two galaxies strengthens the Whirlpool's density waves and triggers bursts of star formation. The enhanced blue light we observe from the spiral arms partially reflects these interaction-driven star formation episodes. Without NGC 5195, the Whirlpool would still be a spiral galaxy, but its arms would likely be less prominent, less organized, and less photogenic. What appears in photographs as a small galaxy touching a spiral arm actually represents a complex three-dimensional geometry that two-dimensional images cannot convey. NGC 5195 currently lies behind the Whirlpool's disk, not beside it, as the apparent connection suggests. We are looking through the Whirlpool at its companion, seeing the smaller galaxy projected against the larger one from our particular viewing angle. The apparent contact between the companion and the spiral arm is a projection effect. The two objects are separated by tens of thousands of light-years along our line of sight, far enough apart that stars from one galaxy do not intermingle with stars from the other. But gravitational forces operate across vast distances. The companion does not need to physically touch the whirlpool to affect its structure. Gravity reaches across the gap between them, linking the two systems in their ongoing interaction. This orbital dance will continue for billions of years, with the companion completing multiple additional passages through or near the whirlpool's disk. Each encounter will further disturb both galaxies, eventually driving them toward complete merger. The beautiful spiral structure that makes M51 famous will not survive this process. Merging galaxies undergo violent gravitational rearrangement that destroys ordered disk structures and produces elliptical or irregular remnants. The merger timescale is difficult to predict, precisely because it depends on orbital parameters that remain uncertain. But the outcome is not in doubt. Gravitationally bound galaxy pairs inevitably merge. Energy dissipation through tidal interactions gradually shrinks their orbits until the systems combine. The whirlpool and its companion will eventually become a single larger galaxy, containing the combined stellar populations of both current systems. The interstellar medium, filling the space between the whirlpool stars, contains far more than empty vacuum. The term space suggests emptiness, but galactic interiors harbour significant quantities of gas and dust distributed throughout the stellar disk. This material provides the raw ingredients for ongoing star formation, the feedstock continuously processed through the density wave assembly line. Vast clouds of molecular hydrogen drift through the spiral arms, invisible to optical telescopes but detectable through radio observations. Hydrogen molecules emit radiation at characteristic radio wavelengths when disturbed by collisions or other energetic processes. Radio telescopes tuned to these frequencies can map molecular gas distributions throughout external galaxies, revealing where the raw material for future stars concentrates. In the whirlpool, molecular hydrogen concentrates along the spiral arms in patterns that beautifully confirm density wave theory. The gas does not distribute uniformly throughout the disk. It piles up in the compression zones, exactly where theory predicts it should accumulate. The correspondence between radio maps of molecular gas and optical images of spiral arms provides powerful evidence that density waves genuinely operate as theoretical models describe. Dust particles mixed with the gas create the dark lanes visible in optical photographs. These microscopic grains, typically smaller than 1 micron in diameter, form from heavy elements ejected by dying stars. Despite their tiny individual sizes, dust grains accumulate over interstellar distances to significantly affect the transmission of light. A dust cloud that appears tenuous by laboratory standards can block substantial fractions of background starlight when that light must traverse dozens of light-years of dusty space. The dark dust lanes threading through the whirlpool's spiral arms mark regions of high gas density where dust concentrations reach their peaks. These lanes appear dark, not because they emit less light than surrounding regions, but because they absorb light from stars behind them. We see shadows cast by intervening dust against the bright stellar background. The lanes trace the inner edges of spiral arms where gas first encounters density wave compression, exactly as theoretical models predict. Dust plays essential roles beyond mere obscuration. The surfaces of dust grains provide sites where complex molecules can form through chemical reactions that cannot occur efficiently in gas phase environments. Atoms landing on grain surfaces can migrate across the surface, encounter other atoms, and combine into molecules that would be unlikely to form through random gas phase collisions. Some astrobiologists speculate that dust grain surfaces may have contributed to the chemical complexity necessary for life's origin. Dust also facilitates star formation by helping molecular clouds radiate away heat. Collapsing gas clouds heat up as gravitational energy converts to thermal energy. This heating creates pressure that resists further collapse. Dust grains help by absorbing thermal energy from the gas and re-radiating it as infrared light that can escape the cloud. This cooling allows collapse to continue, enabling cloud fragments to contract to stellar densities. Chemical enrichment processes have been operating in the whirlpool for billions of years, gradually transforming the composition of the interstellar medium from primordial simplicity to present-day complexity. The story of this enrichment connects directly to the life cycles of stars across cosmic time. The first generation of stars in any galaxy formed from primordial material left over from the Big Bang. This material consisted almost entirely of hydrogen and helium, the two lightest elements, with trace amounts of lithium. No heavier elements existed anywhere in the young universe. Carbon, oxygen, nitrogen, iron, and all the other elements essential for rocky planets and biological chemistry had not yet been created. Those first-generation stars changed everything through nuclear fusion. Deep in stellar cores, hydrogen nuclei fused to form helium, releasing energy that made stars shine. In more massive stars, fusion continued beyond helium, building carbon, oxygen, and progressively heavier elements through successive fusion reactions. The most massive stars eventually exploded as supernovae, scattering their heavy element-enriched material throughout surrounding space. This scattered material mixed with remaining primordial gas, slightly enriching its composition. The next generation of stars formed from this modestly enriched mixture. These second-generation stars contained small amounts of heavy elements inherited from their predecessors. When they died, they contributed additional heavy elements to the interstellar medium. Each stellar generation processes material through nuclear fusion and returns enriched products to the galactic environment. Over billions of years and countless stellar life cycles, the heavy element content of the interstellar medium has gradually increased. The gas and dust in the whirlpool today contains elements forged in stellar cores across the galaxy's entire history, the accumulated contribution of countless stars that lived and died before the material now entering star formation was assembled. The elements necessary for rocky planets and biological chemistry accumulated through this process of stellar nucleosynthesis and dispersal. The carbon in organic molecules, the oxygen in water, the nitrogen in proteins, the iron in blood, and the calcium in bones all originated in stellar interiors. When we observe the whirlpool's spiral arms, we see regions where this enriched material is currently being processed into new stars that will someday contribute their own heavy elements to future generations. The color gradient visible across the whirlpool reveals its star formation history painted in stellar hues. Different regions of the galaxy display distinctly different colors that correspond to different stellar populations with different characteristic ages. The spiral arms glow with brilliant blue light dominated by young hot stars. These massive stars formed within the past few million to tens of millions of years from gas. Recently processed through density wave compression, their surfaces reach temperatures of 20,000 degrees or more, causing them to emit most of their light at short blue wavelengths. Despite being individually rare, these luminous blue giants outshine their countless smaller neighbors, dominating the visual appearance of actively star-forming regions. But these blue giants live fast and die young. Stars more than about 8 times the mass of our Sun exhaust their nuclear fuel in just a few million years. A cosmic eye blink compared to the Sun's 10 billion year lifetime. When their fuel runs out, massive stars explode as supernovae, returning much of their mass to the interstellar medium and leaving behind neutron stars or black holes. The blue stars illuminating the whirlpool's arms will be gone long before their parent galaxy completes another rotation. The yellowish central bulge of the whirlpool tells a different story. This region contains ancient stars formed billions of years ago when the galaxy was young. These old stars have exhausted the hydrogen fuel in their cores and evolved into red giants, subgiants, and other late-stage configurations. Their cooler surface temperatures produce light that peaks at yellow, orange, and red wavelengths rather than blue. The bulge appears yellow because it contains predominantly old stellar populations with very little ongoing star formation. The gas that might fuel new stars has been consumed or expelled. The density waves that organize arm structure do not penetrate efficiently into the bulge region. Without fresh star formation to supply short-lived blue giants, the bulge's appearance is dominated by long-lived, cool, evolved stars. The contrast between blue arms and yellow bulge reveals the spatial distribution of star formation activity. Arms are where new stars form. The bulge is where star formation ended long ago. Interarm regions show intermediate colors, reflecting mixtures of stellar populations with various ages. The entire galaxy becomes a canvas painted with stellar evolution, different colors revealing different chapters in the ongoing story of stellar birth and death. Differential rotation governs how stars move through the whirlpool on their endless journeys around the galactic center. Understanding this rotation is essential for appreciating why spiral structure exists and how the density wave mechanism operates. A star orbiting near the galactic center experiences strong gravitational attraction from the concentrated mass in the inner galaxy. This strong gravity requires high orbital velocities to maintain a stable orbit. Inner stars circle the galaxy quickly, completing full orbits in roughly 100 million years. The actual orbital period depends on distance from the center and the enclosed mass distribution, but inner orbits are consistently faster than outer ones. A star in the outer spiral arms feels weaker gravitational attraction because less galactic mass lies interior to its orbit. Weaker gravity requires lower orbital velocities. Outer stars take much longer to complete their galactic circuits, perhaps 300 million years or more for stars near the visible edges of the disk. This difference in orbital periods creates the differential rotation that would destroy material spiral arms. Inner regions rotate faster and gradually pull ahead of outer regions. If spiral arms were composed of specific stars traveling together, the inner portions would race ahead while the outer portions lagged behind. The arms would wind up like an overwound clock spring. Density wave theory resolves this paradox by recognizing that spiral arms are patterns rather than material structures. The wave pattern rotates at a single characteristic speed throughout the disk. Matter flows through the pattern at different rates depending on position, but the pattern itself maintains coherent rotation. The wave does not wind up because it rotates as a whole, not differentially. The pattern speed of the whirlpool's density waves lies between the fast rotation of inner stars and the slow rotation of outer stars. At a specific radius called corrotation, stars orbit at exactly the same speed as the pattern. Inside corrotation, stars orbit faster than the pattern and overtake the density waves from behind. Outside corrotation, stars orbit slower than the pattern and are overtaken by the approaching density waves. These dynamics explain why the star formation assembly line progresses in the direction it does along spiral arms. Gas approaches density waves from specific directions depending on whether it lies inside or outside corrotation. The sequential stages of star formation arrange themselves along the arm in predictable patterns that depend on the local relationship between material orbits and pattern rotation. The whirlpool's prominent spiral structure results from the combination of intrinsic density wave mechanisms and external gravitational enhancement from the interacting companion galaxy. The density waves would exist without NGC 5195, but they would be weaker and less organized. The companion's repeated passages have amplified the waves to the spectacular prominence we observe today. This combination of internal dynamics and external perturbation makes the whirlpool a particularly valuable laboratory for studying spiral structure. The enhanced waves are easier to observe and measure than the weaker patterns in isolated galaxies. The ongoing interaction provides a natural experiment in how galactic encounters affect disk structure. Scientists can compare the whirlpool to less disturbed spirals and quantify how gravitational perturbations modify wave behavior. The anatomy of the whirlpool reveals cosmic physics operating across scales from microscopic dust grains to 100,000 light-year galactic disks. Density waves, differential rotation, gravitational interactions, and chemical enrichment combine to produce the spectacular structure that has fascinated observers since Lord Rosse first resolved the spiral pattern nearly 2 centuries ago. But the visible structure represents only part of the story. Hidden within and around the luminous spiral lies matter we cannot directly observe, forces we do not fully understand, and phenomena that continue to surprise astronomers with each new generation of instruments. The secrets concealed within the Whirlpool's elegant arms await examination. At the exact center of the Whirlpool Galaxy lurks a monster. Not a monster of science fiction, but something far stranger and more terrifying than any creature human imagination has conjured. A supermassive black hole containing approximately 1 million times the mass of our Sun compresses into a region smaller than our solar system. This gravitational beast warps space and time in ways that challenge human comprehension, creating conditions where the familiar laws of physics twist into configurations that defy everyday intuition. A black hole forms when matter compresses beyond a critical threshold. Every object has an escape velocity, the speed required to break free from its gravitational grip. Earth's escape velocity is roughly 25,000 miles per hour. The Sun's escape velocity at its surface exceeds 1 million miles per hour. As objects become more massive or more compact, their escape velocities increase. A black hole is simply an object so massive and so compact that its escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape from within a black hole's event horizon. Not matter, not radiation, not information of any kind. The event horizon marks a boundary of no return, a spherical surface surrounding the singularity where gravitational imprisonment becomes absolute. Anything crossing this threshold joins the black hole's mass permanently, adding to the gravitational prison from which it can never escape. The supermassive black hole at the Whirlpool center contains roughly 1 million solar masses. To visualize this, imagine taking our Sun, an object already so massive it contains 99.8% of all matter in our solar system, and multiplying it by 1 million. Now compress all that mass into a region so small that its event horizon would fit comfortably between the Sun and Jupiter. The density, implied by this compression, produces gravitational forces that bend light, slow time, and tear matter apart at the atomic level. 1 million solar masses actually places the Whirlpool's black hole in the lower range of supermassive black holes found in galaxy centers. The black hole at the center of our own Milky Way, called Sagittarius A*, contains approximately 4 million solar masses. The giant elliptical galaxy M87 harbors a black hole exceeding 6 billion solar masses, thousands of times more massive than the Whirlpool's central engine. Some of the most extreme supermassive black holes detected approach 100 billion solar masses. Monsters so large they challenge theoretical models of how such objects could form. But even 1 million solar masses represents gravitational forces utterly beyond human experience. Standing at a safe distance from the Whirlpool's central black hole, you would observe bizarre phenomena predicted by Einstein's general relativity. Light from distant stars would bend around the black hole, creating distorted images and gravitational lensing effects. Clocks near the black hole would tick more slowly than clocks farther away, time itself stretched by intense gravity. Approaching too closely would trigger tidal forces strong enough to tear any material object into streams of plasma spiraling toward the event horizon. The black hole at the Whirlpool center does not sit passively at the galactic core, like some dormant predator waiting for prey. It actively feeds on surrounding material, producing energetic emissions detectable across 23 million light-years of cosmic space. Gas and dust drifting too close to the black hole cannot simply fall straight in. Conservation of angular momentum forces the material into spiraling orbits, forming a rotating accretion disk around the event horizon. Within this accretion disk, matter heats to extreme temperatures through friction and compression. Different orbital layers move at different speeds, rubbing against each other and converting orbital energy into thermal energy. The innermost regions of the disk reach temperatures of millions of degrees, hot enough to strip atoms into plasma and emit radiation across the electromagnetic spectrum. X-rays pour from the superheated material, gamma rays flash from the most energetic regions, and radio waves emanate from charged particles spiraling in magnetic fields. This accretion activity classifies the Whirlpool as a Seyfert galaxy, specifically a Seyfert Type II. The Seyfert classification, named after astronomer Carl Seyfert, who first identified this category in 1943, describes galaxies with unusually bright central regions powered by actively feeding supermassive black holes. The distinction between Seyfert types depends primarily on viewing angle rather than intrinsic differences in the central engines. Seyfert Type 1 galaxies show their accretion disks directly, allowing observers to see broad emission lines from rapidly moving gas close to the black hole. Seyfert Type 2 galaxies, like the Whirlpool, have their central regions partially obscured by intervening dust. We observe the active nucleus through a partial veil that blocks some radiation while allowing other wavelengths to escape. The obscuring material likely forms a torus, a donut-shaped structure surrounding the accretion disk and blocking direct views from certain angles. From our vantage point 23 million light-years away, the Whirlpool's central black hole appears as a Seyfert II because our line of sight passes through this dusty torus. If we could somehow move to a different viewing angle, looking down on the system from above the torus, the same galaxy would appear as a Seyfert Type 1. The underlying physics is identical, only our perspective differs. X-ray telescopes reveal what optical instruments cannot penetrate. The Chandra X-ray Observatory, launched in 1999, has observed the Whirlpool Center extensively over more than 2 decades of operation. Chandra detects high-energy radiation that passes through dust clouds opaque to visible light, revealing the violent processes occurring near the event horizon. These observations show intense X-ray emission from the immediate vicinity of the black hole, precisely where theory predicts accretion heating should produce high-energy radiation. The X-ray luminosity varies over time as the accretion rate fluctuates, sometimes brightening when fresh material falls into the feeding zone, sometimes dimming when the local supply runs low. This variability confirms that the central source is compact, small enough that changes can propagate across it on human timescales. Chandra observations also reveal jets of material shooting outward from the central regions. Not everything falling toward a black hole successfully enters the event horizon. Some material gets redirected by magnetic fields, threading the accretion disk, launching along the black hole's rotational axis at velocities approaching the speed of light. These jets carry energy enormous distances from the galactic core, inflating bubbles of hot gas that interact with surrounding galactic matter. The jets from the Whirlpool's black hole extend thousands of light-years from the galactic center, depositing energy into the interstellar medium and influencing conditions far from the nucleus. Hot gas bubbles created by jet activity can suppress star formation by heating molecular clouds beyond the temperatures where gravitational collapse occurs. Alternatively, jet-driven shocks can compress gas clouds and trigger star formation. The net effect depends on local conditions and remains an active area of research. A small disk of dust orbits close to the central black hole at tremendous speeds. Hubble Space Telescope observations resolved this nuclear dust disk, revealing its orientation and rotation. Measuring the rotation velocity reveals the central mass through straightforward gravitational physics. The faster material orbits at a given distance, the more massive the central object must be to provide the gravitational force keeping that material in orbit. The relationship is precise and mathematical. Orbital velocity squared times orbital radius divided by the gravitational constant equals the enclosed mass. By measuring velocities and distances for the nuclear dust disk, astronomers calculated the black hole mass independently of any assumptions about accretion, luminosity, or X-ray emission. The result confirmed the approximately 1 million solar mass estimate derived from other techniques, building confidence that we understand the Whirlpool central engine correctly. But the supermassive black hole, despite its fearsome properties, accounts for only a tiny fraction of the Whirlpool's total mass. 1 million solar masses sounds enormous, and it is by any human standard. But the galaxy as a whole contains over 100 billion stars, plus vast quantities of gas and dust. The black hole represents less than 100,000th of the galaxy's visible mass. It dominates the galactic center, but contributes negligibly to the overall gravitational budget governing the galaxy's structure. The true dominant mass component cannot be seen at all. Visible matter accounts for only a fraction of the mass governing the whirlpool's structure and dynamics. Astronomers discovered this disturbing fact through careful measurements of how stars move through the galaxy. The technique, called rotation curve analysis, reveals the distribution of mass throughout galactic disks, regardless of whether that mass emits detectable radiation. The principle behind rotation curves is straightforward. Stars orbit galactic centers at velocities determined by the total mass interior to their orbits. More interior mass means stronger gravitational attraction, which requires faster orbital velocities to maintain stable circular orbits. By measuring stellar velocities at various distances from the galactic center, astronomers can map how mass distributes throughout the galaxy. If galaxies contained only the matter we can see, stars and gas and dust, then rotation curves should follow a predictable pattern. Near the galactic center, where most visible mass concentrates, orbital velocities should be high. Moving outward into regions of lower stellar density, velocities should decrease as the enclosed mass grows more slowly. Eventually, in the outermost regions where stars become sparse, orbital velocities should decline roughly as the square root of distance, following what astronomers call Keplerian rotation. The Whirlpool's rotation curve does not follow this prediction. Observations reveal that outer stars orbit far faster than they should based on visible matter alone. These stars should barely be gravitationally bound to the galaxy, moving at speeds just above escape velocity, ready to drift off into intergalactic space at the slightest perturbation. Instead, they orbit at speeds requiring enormous additional gravitational attraction from mass we cannot observe. This discrepancy between predicted and observed rotation appears in virtually every spiral galaxy astronomers have studied. The Whirlpool is not unusual in this regard. It simply provides another clear example of a phenomenon that has revolutionized our understanding of cosmic structure. Galaxies contain far more mass than their visible components suggest. Dark matter provides the missing mass. This invisible substance does not emit light at any wavelength. It does not absorb light or scatter light or interact with electromagnetic radiation in any detectable way. Dark matter neither glows nor casts shadows. It passes through ordinary matter like a ghost, interacting only through gravity and possibly through weak nuclear forces that have so far evaded detection. The name dark matter reflects our ignorance rather than any intrinsic property. The substance is not dark in any meaningful physical sense. It is simply invisible to every detection method humans have devised. We know dark matter exists because we observe its gravitational effects on visible matter. We know approximately how much dark matter exists because we can measure those gravitational effects quantitatively, but we do not know what dark matter actually is. Computer models of galactic structure suggest that dark matter outweighs visible matter in the whirlpool by ratios of approximately 10:1. For every star shining in the galaxy, for every gas cloud drifting through spiral arms, for every dust grain obscuring background light, 10 times more mass exists in a form completely invisible to our instruments. The beautiful spiral structure we photograph represents merely the luminous frosting on an invisible gravitational cake. The dark matter likely forms an enormous halo extending far beyond the visible galaxy. While the stellar disk spans 60,000 to 90,000 light-years, the dark matter halo may extend 2 or 3 times farther in every direction. This invisible sphere of mass provides the gravitational container within which visible matter concentrates. Stars and gas fall toward the center of the dark matter distribution, accumulating where the gravitational potential reaches its minimum. The visible galaxy we photograph floats within this dark matter halo, like a glowing core embedded in invisible surroundings. The spiral arms, the central bulge, the stellar disk. All the luminous structures that make the whirlpool beautiful represent only the innermost concentration of matter within a far larger invisible structure. The edges of the dark matter halo lie so far from the galactic center that they contain essentially no stars, no gas, no dust, nothing but the mysterious substance that dominates cosmic mass budgets. Dark matter also governs how galaxies interact with each other. When the Whirlpool and NGC 5195 approach each other in their ongoing gravitational dance, their dark matter halos begin interacting long before their visible components come close. The halos are so much larger than the luminous galaxies that dark matter perturbations precede stellar interactions by enormous margins. Gravitational forces between these invisible concentrations drive the encounter and determine its character. The dark matter halos interpenetrate, passing through each other because dark matter does not collide in the conventional sense. It responds only to gravity, not to contact forces. While the halos overlap, gravitational torques transfer angular momentum between the systems, altering their orbits and creating the perturbations that enhance spiral structure in the Whirlpool's visible disk. Understanding the Whirlpool's dark matter distribution helps explain why its interaction with NGC 5195 produces the spectacular patterns we observe. The strength and duration of gravitational perturbations depend on the total mass involved, not just the visible mass. Models incorporating dark matter reproduce the observed spiral enhancement far better than models considering only stars and gas. Dark matter is essential for explaining the Whirlpool's current appearance. Scientists continue searching for direct detection of dark matter particles. Underground laboratories house detectors designed to register the rare interactions that might occur when dark matter particles pass through ordinary matter. Particle accelerators attempt to create dark matter under controlled conditions. Space telescopes search for signatures of dark matter annihilation in regions of high dark matter density. So far, no experiment has achieved definitive detection. The nature of dark matter remains one of the most significant unsolved problems in modern physics. We know it exists. We know approximately how it distributes through galaxies and clusters. We know it dominates the mass budget of cosmic structures. But we do not know what particle or field constitutes this mysterious substance. The Whirlpool Galaxy, like every galaxy we study, reminds us that most of the universe remains invisible and unknown. The Whirlpool has experienced unusual supernova activity that continues to puzzle astronomers and generate debate about star formation rates in interacting galaxies. 3 stellar explosions occurred within a span of just 17 years, a clustering that significantly exceeds statistical expectations for a galaxy of this size and luminosity. Supernovae are rare events even in galaxies containing billions of stars. The typical supernova rate for a spiral galaxy like the Whirlpool is roughly 1 explosion per century. Most stars are not massive enough to explode. Only stars exceeding approximately 8 times the mass of our Sun end their lives in supernova explosions. These massive stars are intrinsically rare, forming only a small percentage of stellar populations. They also live fast and die young, burning through their nuclear fuel in millions rather than billions of years. Against this statistical background, 3 supernovae in 17 years represents remarkable activity. The first of this cluster, designated Supernova 1994, appeared in April of that year. Amateur astronomers monitoring the Whirlpool detected a new point of light that had not appeared in previous observations. Professional follow-up confirmed the discovery as a type-like supernova, a category indicating that a massive star had exploded after losing its outer hydrogen and helium layers before core collapse. Supernova 1994 reached peak brightness of approximately magnitude 13, easily visible in amateur telescopes despite its location 23 million light-years away. At maximum light, the explosion briefly rivaled the combined luminosity of millions of ordinary stars. The supernova faded over subsequent months as the expanding debris cloud cooled and thinned, eventually disappearing below detection thresholds. 11 years later, supernova 2005 CS appeared in June 2005. This event was classified as a Type IIP supernova, indicating a massive red supergiant star that retained its hydrogen envelope until core collapse. The explosion was somewhat fainter than its predecessor, reaching approximately magnitude 14 at maximum. Detailed observations tracked the light curve and spectral evolution, providing data about the progenitor star and explosion mechanism. The third explosion, supernova 2011 DH, appeared in May 2011. This event attracted exceptional scientific attention because astronomers successfully identified the probable progenitor star in archival Hubble Space Telescope images taken before the explosion. A yellow supergiant, visible in pre-explosion photographs at the supernova's precise location, disappeared in post-explosion images, presumably destroyed in the blast. Identifying supernova progenitors directly is extremely valuable for understanding which types of stars produce which types of explosions. Theoretical models predict relationships between progenitor properties and supernova characteristics, but testing these predictions requires observing the same star both before and after it explodes. The Whirlpool's proximity and extensive archival coverage made this rare identification possible. Supernova 2011 DH was initially classified as a Type 2b event, indicating some hydrogen in the spectrum but less than typical Type 2 supernovae. The yellow supergiant progenitor was somewhat surprising, as many models predicted blue supergiants or Wolf-Rayet stars for this supernova type. The discrepancy sparked productive scientific debate about stellar evolution and mass loss processes in the years before core collapse. Why has the Whirlpool experienced so many supernovae in such a short time? Some astronomers attribute the clustering to statistical fluctuation, nothing more than random chance producing an unlikely but not impossible sequence. Supernova rates fluctuate naturally over time. A galaxy might go decades without an explosion, then experience several in quick succession, with the long-term average remaining consistent with predictions. Other astronomers suggest the gravitational interaction with NGC 5195 has enhanced star formation to levels producing more supernovae than isolated galaxies experience. Enhanced star formation rates mean more massive stars forming per unit time. If the Whirlpool has been forming stars at elevated rates for hundreds of millions of years due to interaction-driven density wave enhancement, then the galaxy should also be experiencing elevated supernova rates. The enhanced star formation explanation is physically plausible. Observations confirm that the Whirlpool's spiral arms glow with particularly intense blue light from young stellar populations. The interaction with NGC 5195 has demonstrably enhanced density waves and triggered star formation activity. Connecting this enhanced star formation to enhanced supernova rates requires only straightforward stellar evolution. Massive stars that formed tens of millions of years ago in interaction-triggered starbursts are reaching the ends of their lives and exploding today. Each supernova seeds the interstellar medium with heavy elements created during the progenitor star's life and synthesized in the explosion itself. Elements up to iron form through nuclear fusion in stellar cores. Elements heavier than iron form through rapid neutron capture during the supernova explosion. When floods of neutrons bombard atomic nuclei and build up mass numbers faster than radioactive decay can reduce them, the heavy elements scattered by supernovae mix with surrounding gas and eventually incorporate into subsequent generations of stars and planets. The three recent supernovae in the Whirlpool have each contributed to the galaxy's chemical enrichment, adding their products to the interstellar medium from which future stars will form. Planets forming around stars that condense from this enriched material will inherit the chemical legacy of these explosions. Perhaps the most remarkable discovery in the Whirlpool Galaxy involves something far smaller and more intimate than supernova explosions. In 2021, astronomers reported detecting what may be the first planet ever found outside our own Milky Way galaxy. The claim, if correct, extends planetary science across intergalactic distances for the first time in human history. Finding planets at extragalactic distances presents extraordinary challenges that initially seemed insurmountable. Standard exoplanet detection methods rely on observing tiny effects that planets produce on their host stars. The transit method watches for slight dimming when a planet passes in front of its star, blocking a fraction of the starlight. The radial velocity method tracks tiny wobbles in stellar motion caused by gravitational tugging from orbiting planets. Both methods require precision measurements of individual stars. But individual stars in the Whirlpool Galaxy cannot be resolved and studied with the precision needed for conventional exoplanet detection. At 23 million light-years distance, even the Hubble Space Telescope sees only the brightest individual stars as barely resolved points. The vast majority of M51's stellar population blends together into unresolved background light. Detecting the tiny signals that portray planetary companions is simply impossible for these distant, unresolved sources. X-ray binary systems offered an unexpected pathway around this limitation. These exotic systems contain a compact object, either a neutron star or stellar mass black hole, gravitationally bound to a normal companion star. Matter flows from the companion onto the compact object, spiraling inward through an accretion disk, similar to but much smaller than those around supermassive black holes. The accretion process heats in falling material to millions of degrees, producing intense X-ray emission from a very compact region. The key insight, enabling extragalactic planet detection, is that X-ray binary emission comes from an extremely small source. The accretion disk around a stellar mass compact object measures only thousands of kilometers across, far smaller than the millions of kilometers spanned by ordinary stellar photospheres. When a planet passes in front of such a compact X-ray source, it can potentially block the entire emission region rather than just a small percentage of an extended stellar disk. A planetary transit across a normal star like our Sun blocks perhaps 1% of the starlight, a small but measurable dimming. A planetary transit across an X-ray binary accretion disk can block 100% of the X-ray emission if the planet is large enough and the geometry favorable. This produces a vastly more dramatic signal, potentially detectable even at extragalactic distances where conventional transit photometry fails. Astronomers using the Chandra X-ray Observatory examined archival observations of X-ray binary systems in the Whirlpool Galaxy, searching for evidence of this hypothesized planetary transit signature. They found exactly such a signal in a system designated M51ULS1. The M51ULS1 system normally emits strong X-ray radiation, consistent with active accretion onto a compact object. The companion star is massive, approximately 20 times the mass of our Sun, providing a steady supply of material to feed the accretion process. The compact object is either a neutron star or stellar mass black hole, though current observations cannot distinguish between these possibilities. During one Chandra observation spanning several hours, the X-ray emission from M51ULS1 dropped to zero. The source simply turned off for approximately 3 hours before returning to normal brightness. The transition was not gradual. The source went from full brightness to undetectable in a relatively short time, remained off for about 3 hours, then returned to full brightness with similar abruptness. The research team, led by Rosanne DiStefano of the Harvard-Smithsonian Center for Astrophysics, analyzed various possible explanations for this peculiar behavior. Could a passing cloud of gas or dust have absorbed the X-rays? The characteristics of the dimming event did not match what gas absorption would produce. Could the X-ray source itself have undergone intrinsic variability, temporarily shutting off accretion? The timescale and profile of the event did not match known variability patterns in X-ray binaries. Could the massive companion star have eclipsed the X-ray source during its orbit? Stellar eclipses can indeed produce temporary X-ray dimming in binary systems, but the orbital geometry of M51ULS1 makes this explanation unlikely. The companion star's size and orbital parameters do not match the duration and shape of the observed dimming. After systematically evaluating alternatives, the research team concluded that a planetary transit provided the most consistent explanation for the observed event. An object roughly the size of Saturn, orbiting the X-ray binary at approximately twice Saturn's distance from our Sun, could produce exactly the dimming characteristics Chandra detected. The candidate planet, provisionally designated M51 ULS1b, would occupy a remarkable environment if it exists. It orbits a system containing a stellar corpse, either a neutron star or black hole, plus a massive companion star destined to explode as a supernova within a few million years. The planet presumably formed in a more benign configuration before one of the system's original stars collapsed. It survived whatever cataclysm created the compact object and continues orbiting in the transformed system. Confirmation of this detection faces an enormous practical obstacle. Based on the estimated orbital parameters, the next transit would not occur for approximately 70 years. Scientists working today cannot expect to observe a second transit within their careers, potentially not within their lifetimes. This single transit limitation means the detection cannot be verified through repeated observation. The identification must stand or fall based solely on the quality of the original data and the thoroughness of the alternative explanation analysis. Extraordinary claims require extraordinary evidence, and a single 3-hour event, however well characterized, may not meet that standard for all scientists. Scientific opinion on M51ULS1b remains divided. Skeptics emphasize the unprecedented nature of the claim and the impossibility of confirmation through standard methods. They note that X-ray binary systems are complex environments where unexpected phenomena might mimic planetary transit signatures. Without repeated transits demonstrating a consistent orbital period, they argue, the planetary interpretation remains speculative. Supporters counter that the Chandra data quality is excellent and the analysis rigorous. The research team carefully considered and rejected multiple alternative explanations. The planetary hypothesis provides the most economical explanation for all observed characteristics of the dimming event, demanding higher evidence standards for extragalactic planets than for planets within our galaxy, they suggest, reflects bias rather than scientific rigor. Whether M51ULS1b eventually gains acceptance as a confirmed extragalactic planet or fades into the category of intriguing but unverified claims, the detection demonstrates something profound. Extragalactic planets are potentially observable using existing technology. The methods pioneered in this analysis can be applied to other X-ray binaries in other galaxies. Even if this particular candidate proves spurious, the pathway to extragalactic planetary science has been illuminated. The Whirlpool Galaxy may contain hundreds of billions of planets, orbiting its 100 billion stars. We have potentially detected exactly one of them through a fortunate geometric alignment and an innovative observation strategy. The ratio between what exists and what we can observe illustrates the vast gulf between cosmic reality and human knowledge. Somewhere in that distant spiral, planets orbit alien suns. Some may harbor conditions suitable for life. Some may have developed complex chemistry, biological evolution, perhaps even intelligence. We cannot know. The distances are too vast, the timescales too long, the signals too faint. The Whirlpool's planets remain largely hypothetical, inferred from what we understand about planet formation but hidden from direct observation behind 23 million light-years of cosmic space. The secrets hidden in the spiral extend far beyond what current instruments can reveal. A supermassive black hole actively feeds at the galactic center. Dark matter dominates the mass budget, while remaining completely invisible. Supernovae explode at rates that may reflect interaction-enhanced star formation. Planets possibly orbit in configurations we are only beginning to detect. Each new telescope reveals previously hidden aspects of the Whirlpool's structure. Each new observation technique probes phenomena that earlier methods could not address. The galaxy that Charles Messier dismissed as a nuisance continues yielding discoveries that transform our understanding of cosmic structure and our place within it. What will future instruments find? What secrets remain concealed within the spiral arms, awaiting technology is not yet built and questions not yet formulated? The Whirlpool has surrendered many mysteries over 2.5 centuries of study. It guards many more, patiently waiting for the next generation of observers to ask the right questions with the right tools. In August 2023, the James Webb Space Telescope released images of the Whirlpool Galaxy that fundamentally changed how scientists understand this familiar cosmic landmark. These were not merely sharper photographs of a well-studied object. They revealed aspects of the galaxy that had remained completely hidden from every previous instrument, structures and processes invisible to telescopes observing only visible light. The infrared universe operates by different rules than the optical universe we perceive with human eyes, and Webb demonstrated what those profound differences mean for understanding how galaxies form, evolve, and create the conditions necessary for planets, and perhaps life. The James Webb Space Telescope represents the most ambitious and expensive astronomical instrument ever constructed by human civilization. Its primary mirror spans 6.5 meters in diameter, composed of 18 hexagonal gold-plated beryllium segments that unfold in space like a technological flower blooming against the cosmic darkness. The gold coating, though only a few atoms thick, optimizes the mirror's reflectivity at infrared wavelengths, where the telescope conducts most of its observations. A tennis court-sized sunshield, consisting of 5 separate layers, protects the instruments from solar radiation, allowing them to cool to temperatures approaching absolute zero. These frigid conditions, colder than any natural environment in our solar system, enable detection of faint infrared radiation that warmer telescopes would drown in their own thermal emissions. Webb orbits the Sun at a special location called the Second Lagrange Point, or L2, approximately 1 million miles from Earth in the direction opposite the Sun. At this gravitationally balanced point, the telescope maintains a constant position relative to both Earth and Sun, allowing its sunshield to permanently block solar radiation while keeping communication antennas pointed toward home. This location keeps the telescope perpetually shielded from the warmth of our star, maintaining the extreme cold necessary for infrared observation. Unlike the Hubble Space Telescope, which orbits just a few hundred miles above Earth's surface and has been serviced multiple times by astronauts aboard the Space Shuttle, Webb operates far beyond any possibility of human repair. If any component fails catastrophically, the telescope cannot be fixed. The mission must function perfectly or not at all. A reality that made its successful deployment in early 2022 one of the most nerve-wracking events in the history of space science. The Whirlpool observations were captured as part of a research program called FEAST, an acronym standing for Feedback in Emerging Extragalactic Star Clusters. Angela Adamo of Stockholm University serves as principal investigator for this ambitious program, which studies one of the most important but poorly understood processes in galactic evolution: how energy released by young stars affects the surrounding interstellar material from which future stellar generations will form. This feedback process operates as a complex loop, connecting stellar birth to stellar death to subsequent stellar birth across billions of years of galactic history. When massive stars form from collapsing clouds of gas and dust, they immediately begin affecting their environments through multiple energetic processes. Intense ultraviolet radiation pours from their surfaces, ionizing and heating surrounding gas. Powerful stellar winds, streams of charged particles traveling at hundreds of miles per second, sweep outward and compress nearby material. When these massive stars exhaust their nuclear fuel after just a few million years of furious burning, they explode as supernovae, releasing more energy in seconds than our Sun will produce throughout its entire 10 billion year lifetime. This feedback can either suppress further star formation by dispersing the raw materials needed for gravitational collapse, or It can trigger new star formation by compressing nearby gas clouds beyond the threshold where gravity overwhelms pressure. The net effect depends on local conditions in ways that theoretical models struggle to capture accurately. The Whirlpool provided an ideal target for studying stellar feedback because its favorable orientation offers clear views across an entire galactic disk without the obscuring dust lanes that complicate observations of edge-on systems. Rather than peering through overlapping spiral arms and intervening material as we would if viewing the galaxy from the side, we look down on the Whirlpool's spiral structure from above, observing feedback processes operating across thousands of light-years of actively star-forming territory simultaneously. The galaxy's vigorous star formation activity, significantly enhanced by the ongoing gravitational interaction with its companion, provides abundant examples of feedback in various evolutionary stages, from the earliest compression of molecular clouds to the final dispersal of birth material around mature stellar clusters. Webb observes primarily in infrared wavelengths, using two complementary instruments designed for different portions of the infrared spectrum. The near-infrared camera, called NIRCam, detects radiation at wavelengths slightly longer than visible red light, extending from approximately 1 to 5 microns. Human eyes cannot perceive these wavelengths, but they carry crucial information about stellar populations and dust distributions that optical observations completely miss. The mid-infrared instrument, called MIRI, observes at still longer wavelengths ranging from 5 to 28 microns. These wavelengths correspond to thermal emission from warm dust, the characteristic infrared glow produced by microscopic grains heated to temperatures of hundreds of degrees by radiation from nearby stars. Together, these instruments peer through dust clouds that completely block visible light, revealing structures and processes hidden from optical telescopes like Hubble for the entire history of astronomical observation. The infrared view transforms our understanding of the Whirlpool's spiral arms in ways that surprised even the most experienced researchers who have spent careers studying this galaxy. Where Hubble showed dark dust lanes, interrupting the bright stellar background like rivers of shadow cutting through fields of stars, Webb revealed those same regions as complex luminous structures with their own intricate internal organization. The dust is not simply obscuring material passively blocking our view of more interesting phenomena occurring behind it. The dust itself participates actively in the physical and chemical processes shaping galactic evolution, playing essential roles in star formation and the synthesis of complex molecules. Dark red regions in the Webb images trace warm dust heated by radiation from nearby stars, forming intricate filamentary networks, threading through the galactic disk like the strands of some cosmic spider web. These filaments connect star-forming regions across enormous distances, suggesting that the interstellar medium possesses far more structure and organization than simpler theoretical models had assumed. Gas and dust do not distribute randomly or smoothly through the galactic volume. They organize into networks and sheets and filaments that channel material flows across vast distances and determine where new stars can form and where the interstellar medium remains quiescent. Understanding this structure has become essential for explaining why stars form in some locations but not in others, despite apparently similar conditions. Brighter red areas in the Webb observations mark locations where complex molecules form on the surfaces of dust grains through chemical processes impossible in the diffuse gas phase. These regions process simpler chemicals into more elaborate compounds, transforming basic elements like carbon, oxygen, and nitrogen into the molecular building blocks of planetary systems and potentially of life itself. Water ice coats, dust grains. In the coldest, densest regions, amino acid precursors and other compounds essential for the biochemistry we know form through reactions catalyzed by grain surfaces acting as microscopic chemical laboratories. The Whirlpool's spiral arms function as cosmic chemistry factories, operating on scales of thousands of light-years, processing simple atoms into the complex molecules that will eventually incorporate into planets, atmospheres, and perhaps living organisms. Orange and yellow hues scattered through the Webb images indicate ionized gas surrounding newly formed stellar clusters, regions where young stars have begun clearing away their birth material through the relentless pressure of intense ultraviolet radiation. The surrounding gas heats to temperatures of thousands of degrees and glows at characteristic wavelengths that Webb's sensitive instruments detect with precision impossible for earlier infrared observatories. These glowing clearings mark transition zones where stellar feedback actively transforms dense star-forming clouds into the more diffuse interstellar medium that fills the space between molecular cloud complexes. The boundaries between these zones reveal the ongoing battle between gravity, trying to collapse gas into new stars, and feedback energy trying to disperse that gas back into the general galactic environment. Perhaps most striking in the Webb images are dark bubbles scattered throughout the spiral arms like holes punched in luminous fabric by some cosmic hole punch. These cavities represent regions where young massive stars have expelled surrounding gas through energetic outflows over millions of years of continuous energy injection. Stellar winds from massive young stars, traveling at velocities of hundreds or even thousands of miles per second, sweep up surrounding material like snowplows, clearing cosmic highways. The swept-up material piles into expanding shells at the bubble edges, while the interiors fill with hot, low-density gas that emits very little infrared radiation, despite its extreme temperatures. This creates apparent voids in the glowing dust distribution, dark spots marking where stellar feedback has most dramatically sculpted the interstellar medium. Stellar feedback shapes the interstellar medium into complex structures that previous generations of telescopes could not resolve regardless of how long they observed. The bubbles visible in Webb images vary dramatically in size, from compact cavities spanning just a few light-years, cleared by individual massive stars, to enormous voids hundreds of light-years across, carved by the combined output of large stellar associations containing dozens or hundreds of massive stars working together over millions of years. Some bubbles appear nearly isolated, created by single massive stars or small stellar groups, acting alone in relatively uniform surrounding material. Others overlap and merge into complex interconnected structures where multiple generations of star formation have contributed to reshaping the local galactic environment through cumulative feedback effects. Bright knots of concentrated infrared emissions scattered through the spiral arms mark active star-forming sites where new stellar generations are currently emerging from their dense birth clouds. These knots glow intensely at infrared wavelengths because the forming stars, though still hidden from optical view behind opaque dust cocoons, heat their surrounding material to temperatures, producing strong thermal emission in the wavelength range where Webb observes. The telescope resolves individual star-forming complexes that appeared as single blurred point sources in previous observations, revealing that structures which seemed simple actually contain multiple distinct components at different evolutionary stages. A single bright knot in lower resolution images separates into clusters of protostars, compact dense cores about to begin collapse, and young stellar objects already clearing their immediate surroundings. Connecting filaments of glowing dust thread between the bright star-forming knots in complex networks that resist simple theoretical description. These filaments appear to channel material from the general interstellar medium towards sites of active gravitational collapse, functioning as supply lines, feeding star formation activity across the spiral arms. The spiral density waves compress gas into these filamentary networks as raw material flows through the density enhancement, but the detailed structure visible within compressed regions shows complexity far exceeding what density wave theory alone predicts or explains. Some additional physical process, perhaps magnetic fields threading the interstellar medium or turbulent cascade effects not captured in simpler models, must contribute to organizing gas into filaments rather than smooth sheets or random clumps. The extraordinary detail visible in Webb images approaches what scientists hoped to achieve when the telescope was first conceived during the 1980s and 1990s. Individual star-forming regions across the Whirlpool's disk resolve into complex structures, showing multiple evolutionary stages occurring simultaneously within single fields of view. A Webb image captures infant protostars still deeply embedded in opaque natal cocoons, invisible to optical wavelengths, young stars in the process of clearing their immediate surroundings through radiation and winds, and the compressed shells of gas at bubble edges, where future stellar generations will form when accumulated material becomes gravitationally unstable. Scientists can observe the entire star formation cycle, from initial collapse through final cluster emergence, playing out across the expanse of a single carefully composed observation. For the first time in the history of astronomy, researchers can observe star clusters emerging from their birth clouds in galaxies beyond our immediate local group neighborhood, with sufficient spatial resolution to study the physical processes in meaningful detail. Previous observations of extragalactic star formation necessarily averaged over large areas containing many distinct sites, blending their properties into single unresolved measurements that obscured the diversity of conditions and evolutionary stages present. Webb separates these previously confused sources into individual components, revealing that star formation in external galaxies operates through processes fundamentally similar to star formation in our own Milky Way, but with subtle differences reflecting the varied galactic environments where collapse occurs. Comparing Webb's new observations to earlier Hubble photographs of the same galactic regions demonstrates dramatically how different wavelengths reveal different truths about identical cosmic objects. The two great space telescopes see fundamentally different aspects of physical reality, neither perspective more correct or more fundamental than the other, but instead beautifully complementary in the understanding they provide. Hubble's optical view showed young blue stars whose brilliant visible light dominates short wavelengths, revealing where star formation has recently completed, and massive stellar furnaces now shine without obscuration. Hubble captured pink emission nebulae, where ionized hydrogen gas glows at the characteristic red wavelength of the hydrogen alpha spectral line, marking regions where stellar ultraviolet radiation excites surrounding material into luminous display. Hubble recorded the dark dust lanes threading through spiral arms as shadows and silhouettes against brighter backgrounds, regions where intervening material blocks light from more distant sources. The Hubble view emphasizes the stellar content of galaxies, the accumulated points of light shining most brilliantly at wavelengths near what human eyes would perceive if enhanced to sufficient sensitivity. Webb's infrared view reveals an entirely different galaxy hidden within and behind the optical structures Hubble photographed. Webb shows warm dust distributions that trace where stellar radiation heats interstellar material throughout the spiral arm volume, not just at surfaces visible from our direction. Webb detects embedded stellar populations completely invisible at optical wavelengths, infant and adolescent stars still shrouded within dense birth cocoons that absorb all visible light, while allowing longer infrared wavelengths to escape and reach our detectors. Webb captures the scaffolding of gas and dust connecting star-forming regions across the spiral arms, the material infrastructure through which matter flows toward gravitational collapse that visible light cannot penetrate to reveal. The Webb view emphasizes the interstellar medium, the gas and dust reservoirs from which stars continuously form and into which dying stars return their processed nuclear products. Neither wavelength view is more correct or more fundamental than the other, and neither alone provides complete understanding. Combined thoughtfully, they reveal a far more comprehensive picture of the whirlpool than either telescope provides in isolation. The hot young stars Hubble sees heating surrounding material create the warm dust Webb detects glowing at infrared wavelengths. The dark lanes blocking Hubble's view shine brilliantly when observed with Webb's infrared detectors. Reconstructing how galaxies actually work requires synthesizing observations across the electromagnetic spectrum, building unified models that simultaneously account for optical stellar light, infrared dust emission, radiomolecular line radiation, X-ray hot gas signatures, and every other wavelength window through which the cosmos reveals its nature. The Webb observations also raised new scientific questions, requiring future investigation, demonstrating once again that better observational data often generates more puzzles than it resolves. The bright star-forming knots scattered through the whirlpool's spiral arms appear significantly more numerous and far more spatially organized than theoretical models of galactic star formation had predicted before these. Observations existed. Stars do not form randomly throughout the compressed gas accumulated in density wave regions. They form preferentially at specific locations, arranged in discernible patterns, suggesting coordinating mechanisms operating across hundreds of light years that theorists do not yet fully understand. Star formation appears to proceed in coordinated bursts, affecting extended regions rather than through isolated independent events occurring randomly wherever local conditions happen to favor collapse. When new stars begin forming at one location within a molecular cloud complex, neighboring locations within the same complex also tend to begin forming stars around the same time, rather than at random intervals spread across millions of years. Something synchronizes the gravitational collapse of molecular cloud cores across distances of hundreds of light years, triggering nearly simultaneous star formation across regions far too large for any individual physical process to connect directly. The triggering mechanism, whether propagating shock waves, synchronized turbulent decay, or some other coordinating influence, remains an open problem that Webb observations have dramatically sharpened without yet resolving. Chemical abundance patterns measured across the Whirlpool's disk differ systematically from predictions based on observations of our own Milky Way galaxy, suggesting that the specific galactic environment and interaction history affect chemical evolution in ways astronomers had not previously recognized or incorporated into theoretical models. The Whirlpool's ongoing gravitational interaction with NGC 5195 has apparently influenced not just the visible spiral structure and overall star formation rate, but also the detailed chemical composition of the interstellar medium from which new stars and planets form. Gas mixing between the two interacting galaxies, infall of less chemically enriched material stripped from the smaller companion, and elevated supernova rates from interaction-enhanced star formation may all contribute to producing abundance patterns measurably distinct from isolated galaxies, evolving without external gravitational disturbance. The Whirlpool serves as an essential testing ground for theories of galactic structure and evolution precisely because astronomers have observed it so intensively across so many wavelengths for so many decades. Theoretical predictions that successfully match M51 observations gain credibility as potentially universal principles applicable to spiral galaxies throughout the observable cosmos. Predictions that fail when confronted with detailed Whirlpool data require revision and improvement before they can be trusted to describe galactic processes elsewhere. Each new generation of observations reveals phenomena that previous theoretical frameworks did not anticipate or predict. The universe consistently proves more complex, more varied, and more scientifically interesting than even our most sophisticated models manage to capture. The gravitational interaction between the Whirlpool and NGC 5195 provides an invaluable natural experiment for understanding our own galaxy's distant future. These two interacting systems demonstrate in real cosmic time what happens when spiral galaxies influence each other gravitationally, offering a preview of transformative events that will reshape the Milky Way billions of years from now. The Andromeda Galaxy approaches our Milky Way at approximately 250,000 miles per hour, steadily closing the immense gap between our two spiral systems with every passing year. This approach velocity is not theoretical speculation or model-dependent inference. Astronomers have measured Andromeda's motion directly, using precise Doppler shift observations of light from its stars, definitively confirming that the galaxy moves toward us rather than away. The distance currently separating the Milky Way and Andromeda measures approximately 2.5 million light-years. Despite this seemingly reassuring vastness, the two galaxies are gravitationally bound to each other, locked in a mutual orbital embrace that will inevitably bring them together, regardless of any other cosmic influences. In roughly 4 to 5 billion years, the Milky Way and Andromeda will begin their first close gravitational approach. The galaxies will not collide in the conventional sense of solid objects physically smashing together. Individual stars within galaxies are separated by such enormous distances, typically several light-years between neighbors, that direct stellar collisions will remain extraordinarily unlikely. Instead, the two vast stellar populations will pass through each other, like interpenetrating swarms of fireflies, individual members following altered trajectories but rarely touching. What will collide with tremendous effect is gravity itself. The gravitational fields of both massive galaxies will interact intensely during close approaches, fundamentally reshaping both systems through powerful tidal forces and dynamical friction effects. Stars will be flung onto dramatically new orbits as gravitational perturbations redistribute angular momentum throughout both systems. Gas clouds will compress under tidal squeezing and trigger massive bursts of star formation far exceeding current rates. The beautiful spiral arms characterizing both the Milky Way and Andromeda will stretch, distort, and eventually dissolve entirely as ordered disk rotation gives way to chaotic orbital distributions. The Whirlpool demonstrates, through direct observation, that galactic gravitational interactions need not immediately destroy organized structure. NGC 5195 has been gravitationally interacting with M51 for approximately 500 million years, a temporal span exceeding the entire evolutionary history of complex animal life on Earth. Yet despite this prolonged gravitational disturbance, the larger galaxy retains strikingly beautiful spiral arms that remain among the most frequently photographed celestial structures in all of astronomy. The interaction has enhanced, rather than destroyed, this structure during the current phase of the ongoing encounter. Organized galactic structure can actually be amplified rather than erased during extended gravitational interactions between galaxies. Initial close passes trigger strengthened density waves and intense star formation bursts that make spiral patterns temporarily more prominent and well-defined than they appear in isolated galaxies experiencing no external blah, gravitational influence. The Whirlpool's famous spiral arms owe their spectacular prominence partly to gravitational stimulation from the companion galaxy, repeatedly disturbing the disk. Without NGC 5195 providing periodic gravitational perturbation, M51 would still be a spiral galaxy, but almost certainly a less photogenic and structurally impressive one. Computer simulations modeling the eventual Milky Way-Andromeda merger predict initial encounters that will enhance spiral structure in both galaxies, similar to what we currently observe in the Whirlpool system. Our galaxy's spiral arms may become more visually prominent during early interaction phases, as gravitational perturbations from approaching Andromeda strengthen density wave amplitudes throughout the disk. Star formation rates will likely increase substantially as gas clouds compress in the gravitationally enhanced spiral structure, producing brilliant bursts of blue stellar light before the available gas supply depletes. Multiple close approaches spanning several billion years will gradually transform both galaxies beyond recognition. Each successive passage will trigger additional waves of star formation, consume larger fractions of the remaining interstellar gas supply, and distort the spiral patterns more severely than the previous encounter. The galaxies will separate to large distances after each close approach, but gravitational binding will inexorably draw them back together for subsequent ever closer encounters. Eventually, after billions of years of increasingly intimate gravitational interaction, the two great spiral galaxies will merge completely into a single elliptical galaxy. Astronomers have informally nicknamed this predicted future system Milky Way, combining the names of its parent galaxies into an awkward but descriptively appropriate portmanteau. The beautiful spiral arms characterizing both the modern Milky Way and Andromeda will be completely destroyed during the violent merger process, replaced by a featureless ellipsoidal stellar distribution containing the combined populations of both original systems. Our solar system will almost certainly survive the galactic merger, physically intact despite the dramatic transformation occurring around it. The vast distances separating individual stars ensure that direct stellar collisions will remain vanishingly improbable, even during the most chaotic merger phases. No star from Andromeda will strike our Sun or pass close enough to gravitationally disrupt planetary orbits. The solar system will transit the entire merger as a coherent gravitationally bound unit, its familiar internal structure of planets and moons and asteroids essentially unchanged. What will dramatically change is the solar system's position and trajectory within the merged galactic structure. Gravitational forces during the merger will scatter stars onto entirely new orbits around the combined galactic center, following distributions impossible to predict billions of years in advance. Our Sun might end up in the sparse outer regions of Milky Way, far removed from the dense central stellar concentration. Alternatively, gravitational scattering might fling us onto a highly elongated elliptical orbit that periodically plunges through the crowded galactic core before swinging back out to the periphery. The specific outcome depends sensitively on details of merger geometry and timing that cannot be calculated with useful precision across such enormous timescales. Whether any conscious observers will witness these cosmic transformations remains profoundly uncertain. The Sun will be approaching the end of its hydrogen-burning main sequence lifetime, just as the Andromeda merger begins in earnest. Within approximately 5 billion years, our star will exhaust the hydrogen fuel in its core and begin expanding into a bloated red giant hundreds of times its current diameter. Long before the merger reaches its dramatic conclusion, Earth's oceans will have boiled away into space, and the planetary surface will have become utterly uninhabitable by any life form resembling those we know. The profound isolation inherent in extragalactic observation deserves careful reflection as our conceptual journey to the Whirlpool approaches its conclusion. We can photograph this distant galaxy in exquisite detail. We can analyze its chemical composition. We can measure its motions. We can detect supernovae and possibly planets. But we can never visit, never send probes, never communicate with any life it might contain. Every observation involves looking into the past rather than perceiving present reality. We are forever limited to studying ancient light that departed before our species evolved. The Whirlpool we observe is a historical document preserved in photons from an epoch when our ancestors had not yet developed the neural capacity to wonder about distant lights in the night sky. The continuity of scientific inquiry connecting Charles Messier to the James Webb Space Telescope spans 250 years of sustained human curiosity about the cosmos. Each generation has approached the Whirlpool with better instruments and deeper questions than their predecessors. Each generation has learned something genuinely new while simultaneously recognizing how much remains unknown and perhaps unknowable. We are creatures of one small planet orbiting one average star in one typical galaxy, among hundreds of billions scattered throughout observable space. The Whirlpool reminds us simultaneously of cosmic grandeur and cosmic humility. We have learned to photograph distant spirals, analyze their composition, and deduce their physics through pure intellect applied to ancient light. Yet we remain confined to our tiny cosmic neighborhood, peering outward through instruments that extend our senses while emphasizing just how limited those senses truly are. The journey to the Whirlpool Galaxy is not physical travel across 23 million light-years of cosmic vacuum. Such voyages remain forever impossible given the distances involved and the constraints physics imposes on matter and energy. The journey is entirely conceptual, a progression of understanding extending across centuries of human inquiry and continuing into futures we cannot foresee. 23 million years ago, photons left the Whirlpool Galaxy and began their long journey toward a planet that did not yet exist in its present form. Tonight, that ancient light completes its voyage, entering instruments built by beings who have learned to decode the messages carried across cosmic distances. We extract information from photons that have traveled far longer than our species has existed, reconstructing the structure of a galaxy we can never visit from light that departed before we were born. The Whirlpool waits in the darkness between galaxies, 100 billion stars spinning through space in patterns first recognized by an Irish nobleman peering through the largest telescope his era could construct. Its light spreads outward in all directions across millions of years, most dispersing forever into the void without encountering any observer anywhere. We intercept only a tiny fraction of the photons departing M51, but that fraction suffices to construct images, deduce physics, and contemplate our place in a cosmos far vaster than human minds evolved to comprehend. The journey ends where it began, in wonder. The Whirlpool Galaxy exists whether or not we observe it, whether or not we understand it, whether or not any conscious beings anywhere appreciate its beauty. That we have learned to see it at all represents an improbable triumph of curiosity over cosmic indifference. The light arriving tonight carries whispers of cosmic truth across distances that humble human ambition while inspiring human wonder. 23 million years of travel, 100 billion stars, secrets still hidden in the spiral arms, and questions that will occupy astronomers for generations yet unborn. The whirlpool awaits.